Okay, so let's say that we want to define a line in 3 dimensions. Well, in 2 dimensions, we know that a line is defined as y is equal to mx plus b, where b would be your y-intercept, and m is your slope. Well, in 3 dimensions, we need to have a slope, so to speak, but we do this by actually defining a line to be parallel to a vector. So if we have our 3-dimensional axes here, z, y, x, we can pick a vector like so. So like that, call this vector v, and then we can define a line to be parallel to v, but intercepting another axis or intersecting a point somewhere. And this is how we define lines in 3 dimensions, except we don't define them as y is equal to some function of x and some function of z, or z is equal to some function of x and y. Rather, we define a line to be 3 parametric equations. So we have x is equal to some number, and we'll use a letter, n plus a, well, actually we'll call this n1, plus a times t. Y is equal to n2 plus a2t, and z is equal to n3 plus a3t, where t is any real number. So t is an element of the reals. And what this would do is when you plug in t in each of these equations, it gives you a point in R3 space. So we can use this to find equations of 3-dimensional lines. And so here's a practice problem. Okay, so we'll say find parametric equations of the line. Oops. Find line with y-intercept 3 perpendicular to L1, where L1 is x is equal to minus 2 plus t, y is equal to minus 5 plus 7t, and z is equal to 3 minus 8t. Now I forgot to tell you something up here. These numbers here, actually specify a point. This specifies the point n1, n2, n3, and this line passes through this point. Now this represents vector A, which is equal to A1, A2, and A3. So if you're given an equation of a line, you can find this point on it that it obviously passes through. Typically, we actually plug in a point here. And then we have the vector here that we can determine if we're given the equation of a line. So we can say that the A vector for line 1 is equal to 1, 7, minus 8. And that's just taking the coefficients of the t terms here. And of course, we shouldn't forget t is an element of the reals. So what we do is we now need to find a line perpendicular to this line. And it goes through the y-axis at point 3. So that gives you a point 0, 3, 0, because it's 0 on both x and z, and 3 in the y-axis. So to draw a picture of what's going on here, this helps a lot. We have a point on the y-axis, 3, and I'll draw it in a color that's actually visible, like so. And we have a vector that has x1. No, that's actually not the y-axis. That's the z-axis. So 1, 2, 3. Here's the point that it passes through. 4, 5, 6, 7. x1, z minus 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have a point down here that is actually down here. And that is a vector going to that point. So we need to find the line parallel to that vector, which we'll call L2. And so how do we find, perpendicular to that vector? And how do we find a perpendicular vector? Well, we remember that if perpendicular vectors have a dot product of 0, so A1 dot A2, we'll call this line L2, is equal to 0. So we got to find some vector whose dot product with A1 is 0. Well, 1 times 1 plus 1 times 7 plus 1 times negative 8 is 0. So we could define A2 to be the vector 1, 1, 1. Now that we have this other vector and we have the point here, we can define an equation of the line. So L2 is going to be 3 equations. X is equal to t, y is equal to 3 plus t, and z is equal to t, where t is an element of the reals. So this would be your equation of a line perpendicular to the line parallel to, or perpendicular to the line parallel to vector A1. So L2 is perpendicular to L1. I'll do some more problems like this in hopefully a more clearer fashion in the next video.